class, we were discussing diffraction condition in reciprocal space. So we have in detail understood how we can actually interpret diffraction condition in reciprocal space, and how can we also obtain the value of what you call the uh, intensity of the scattered X-rays. I hope I had also given you the task for calculating, structure factor. We also saw in our yesterday's class what is structure factor and how is structure factor related to the intensity of the scattered X-ray from a crystal or diffracted beam from a crystal. So today we also saw Law's equation in our previous class, right? So today we will see little interpretation part of the Law's equation and how this Law's equation can be interpreted to relate them with the X-ray diffraction pattern observed from a crystalline substance. So I hope you all are aware of what are Law's equation and how they are obtained. So this is your diffraction condition, that is delta K is equal to G. And if we take scalar product of say any of the lattice vectors, say A1, A2 or A3 with on both sides of this equation, then what we arrive at what is called the Law's equation. That has been done. So let us not get into that again. Now let's come to the interpretation part of the Law's equation. Let us pick one of the equation from the previous slide. So what is the physical meaning of this equation? So suppose you have some vector, A1 vector, correct? And dot product of a particular vector with some other vector, actually, say delta K vector here, is equal to some constant, because 2 pi is a constant thing. V1 or new one we were calling it. So this was an integer. So therefore the right hand side in this equation is going to be a constant. Now if we try to imagine any two vectors and their dot product is constant, and the magnitudes of the vectors are also fixed, right? A1 vector is not going to change in its magnitude. Similarly, in delta K as well, there's only change in direction, no change in magnitude, correct? So if this is the situation, under what conditions or how many possibilities are there for those two vectors to satisfy this equation? So basically what is the requirement is that, okay, A1 dot delta K is equal to constant as far as the angle between them remains fixed, because dot product is nothing but product of their magnitudes and the angle between them, cos of angle between them, right? And in this case, since the magnitudes are not changing, so this means that as far as the angle between the two vectors is same, their scalar product is going to remain same. Now let us come to this figure. Here you can try to imagine this line maybe representing a vector, and then these arrows representing, say, delta K vector, let us say. Then what you can see from here is that as long as delta K vector lies on any one of the points on this circle, the angle between A vector and delta K vector is same, isn't it? Because it's something like formation of a cone, and the vector, any vector lying on the surface of the cone originating from its vertex is going to have an angle with this central line, correct? So This means same is going to happen with the X-ray diffraction. I mean, if you incident X-rays on a particular crystal, then X-rays, if you are saying, okay, X-rays are diffracted at a particular angle, say theta, so they are not actually come only at a particular angle, but on actually along a cone, which is having angle theta with respect to, say, something like reference direction. So this is what you say the interpretation of the equation. Here is one example of this same thing. I mean, suppose you have incident beam of X-rays, which is incident on which is incident on a crystal, sorry. And then what you will be finding is depending on okay, which particular plane with rays, you will find out various angles. Correct. So these are giving you angles. Each circle here is actually referring to a particular planes, which corresponds is equal to 2d sine theta. Correct. So accordingly, each circle is representing phi coming from a specific set of planes. So this is one setup for studying X-ray diffraction. So there is another way of looking at X-ray diffraction like this. What if you have a, say, crystalline specimen here, incident X-ray on it, then you can say a photographic plate here somewhere on the way of the diffracted X-ray beam. Then you should see some this kind of circles. These kind of circles, or this is the picture of the photographic plate shown here. So this is like reference beam, which is because some fraction of the incident beam goes like as such directly, right? And then you have these other beams different. Of course, their intensity depends on detailed nature of the constituents of the crystal. That is something which we did yesterday. So this is the kind of pattern you are going to observe. There is another way of looking at X-ray diffraction pattern. So if you have a incident beam of X-rays, so this is a photographic film. Suppose you got a photographic film in some circular shape, then you incident X-ray beam. Here is your crystalline specimen. Then what will happen? One portion of the beam will be crossing through the specimen without any deviation. So this will act as a reference to us, like something like a central spot. And then you will be finding that X-rays will be actually getting scattered at various angles, depending upon at what specific angle diffraction condition is satisfied. So if you now do X-ray diffraction and take this film out and straighten this, so then you may find out a graph between intensity and 2 theta. Correct. So this is your reference angle. Then you can find out what is going to be the angle theta. So you should go back to the this figure. Oh, that's not here. That conventional figure which we had seen, that you had atomic planes, then a perpendicular to the atomic planes, then theta was an angle between the planes, and k vector, right? Theta was angle between the plane and incident direction of the X-rays. So that was theta. So that is how you can get what will be theta here, and then accordingly find out a graph between say incident beam intensity and sorry, the intensity of the X-ray beam which is scattered after diffraction, and then try to plot 2 theta versus intensity. That conventional graph which I had shown for I think so that is how we can do. So nowadays this is not done with the help of photographic films as such, but we have electric sensors. There may be certain crystals which have effect of X-rays on their batteries, and we can record how much is the intensity of X-rays, and that kind of sensor is located in the space, and then measure the intensity of X-rays at various points. So, I mean, having done that, that's the basic idea of this larva equation, and this also related to X reflection only. Now let's see another very interesting aspect of deflection condition in the reciprocatives. I'm sure you all have done that.
So
You
there
understand
is
it very
audio
well.
problem, sir. Audio is not clear. Hello, sir.
Yes.
Hello.
Okay. So
So you are
is
not
it
clearly
audible
audible.
now or what?
No, sir. No, sir. It's not better.
Now
So there is breaking in sound. No?
there
Something
will
like
be
that.
or need to check the end. I mean, I can just try to wait if work is better and see response. So, in case it's better, just let me know. Is there any improvement? My audio or still voice is not okay?
You are not audible, sir.
You are very well audible. Uh, yes, anyone from okay.
Completely lost, sir. We are not able to hear you.
Voice my end. I don't know whether it is on your somewhere it has to be okay both ends. Your voice is coming proper. Yes, is it any okay? I'm not sure. Okay, let us do one thing. Okay, I hope it is improved now. Am I audible now? Okay, sorry for this interruption due to problem with network. Hopefully now it will be fine. So I don't know where you actually was lost from the content. So could we understand this Laue equation and interpretation of Laue equation? You understood the Laue equation or not? So you didn't get Laue. Let's go back again to the Laue's equation. So in case there is a problem, you maybe, I mean, you should immediately report it so that I am not talking to myself only. Well, so that is, I mean, law equation we have done yesterday, I mean, in our previous class or maybe day before yesterday, that how do we arrive at a law equation. and they actually come from the diffraction condition in the reciprocal space. And then if you multiply this diffraction condition in reciprocal space with our lattice vectors, say a1 vector or a2 vector or a3 vector, then you arrive at the Laurent's equation. And then to discuss the physical interpretation of Laurent equations, you may take say one of the Laurent equation. Am I audible now? Is it okay? All right, fine. So now, I mean, and then what is this equation saying? That okay, dot product of any two vectors is constant, right? A1 vector is fixed, and this V1 is some integer. So integer means it is a fixed value, it is a number. Now, if the dot product of any two vectors is constant, what are the possibilities for that to happen? So this is possible when your two vectors are at a specific angle. Now, since in this case the magnitude of the vectors is fixed, delta k changes only in direction, right? It is just change in direction. And similarly, a1 vector is a fixed vector, so it has a fixed magnitude. Therefore, the dot product is going to be if it is a fixed number, then this is possible only when the angle between the two vectors is fixed, isn't it? Because the dot product is like magnitude of one vector, magnitude of second vector into cos of theta. So as long as theta is fixed, the equation is satisfied, correct? So for a particular value of theta, this equation is satisfied. Now, when is this possible, or how many possibilities are there? So basically, let us assume this is representing reference direction, something like say a1 vector. Then all the values of delta k which are at an angle theta will satisfy this equation, correct? And how many possibilities are there? So you can take almost like infinite values of infinite options for delta k. Like okay, all those delta k's which lies on say surface of a cone, all of them makes an angle theta with respect to the reference direction. So basically, if you incident X-rays on a crystal at a specific plane, then you're not going to see X-ray at a particular point only, but along a full circle which is coming through a conical path which is at an angle theta. So that's what is the interpretation of these Laue equations. This is one example, say Debye-Scherrer way of measuring X-ray diffraction pattern. So if you have an X-ray beam and there is a specimen in between, then you will be having different um, angles at which the X-ray intensity will be maximum, correct? So this, if you have a photographic plate on the way, then you will be finding that you will actually be getting a circle on the photographic plate if you have a two-dimensional photographic plate on the way of scattered X-ray. So at a specific angle theta, you will be getting a circle on the photographic plate. Then you may have another angle theta at which again diffraction condition is satisfied, because then that may refer to a different set of planes. And then you may have different circles actually on the photographic plate, which you can then later on interpret. So this is something like reference beam, and then you have circles at different points in space, or circles of which can be interpreted as coming from different planes. So basically, you can and then you can get the information. Now, yes. Hello, am I audible there? Oh, Harish, Sandeep, Rahul,
Yes, yes, sir.
anyone,
You are
Diksha?
audible now, sir.
Oh, I think I had lost connection actually. Somebody called me, so maybe. Okay, fine. If it is fine, so did you get this idea of Laue equation and their interpretation? How we can relate them to diffraction pattern from a crystal? Is this part clear? Is this part okay? Well, let me assume it is okay. Now, another way of looking at this is instead of taking a two-dimensional sheet, if we actually take a strip of photographic plate and then you incident X-rays on your specimen, then one part of it will be going in deviated. Oh, sorry, undeviated, and then some part will be uh, deflected at various angles. I mean, depending upon where the diffraction condition is satisfied. So this thing, I mean, so by straightening this sheet on, say, maybe one single axis, then you can try to get an idea, okay, how or at what angle you are getting the peaks. So this is something like measuring 2 theta versus uh, and say the angle, I mean intensity, 2 theta versus intensity. Now there is also a common question why we plot 2 theta. Usually we plot regarding X-ray diffraction data 2 theta versus intensity. So why 2 theta? This will be okay clear from maybe this graph. So um, this graph also presents another interpretation of diffraction condition in reciprocal space. I hope I am audible there and things are fine so far. Is everything fine?
Yes, sir.
Okay, fine. So now we will be discussing, I mean, this evolved construction, which is another way of looking at diffraction condition from the reciprocal lattice. So here, let us assume that we have, this is actually, these points are representing the reciprocal lattice for a particular real space lattice. Now, since you have already done, we have already discussed that real space lattice, reciprocal lattice. So now I'm sure you all are comfortable with what is reciprocal lattice. Fine. Now, how we can extract information regarding X-ray diffraction from reciprocal lattice is that, okay, let us choose a point, any arbitrary point in reciprocal lattice, and this point is not necessarily the point this point is not necessarily a lattice point in the reciprocal lattice. Fine. So this point is not a lattice point, but we are choosing any arbitrary point in the reciprocal lattice such that if I draw a vector from this point, what is the condition of choosing this point or how we choose this point? We choose this point such that if I draw a vector originating from this vector, this point, say k vector, that vector terminates at any one of the lattice points in the reciprocal lattice. Is that okay? Means we are choosing a point from we are choosing a point in reciprocal lattice and drawing a vector having length equal to k vector, which is nothing but the wave vector for the incident beam, correct? So what will be its length? 2 pi by lambda. Means you have to draw a vector which is depending upon what is the wavelength of the incident X-ray beam, and its direction is directly along the direction of the incident beam. Fine. So means this vector is drawn from a point such that it terminates at one of the lattice points in the reciprocal lattice. Well, that's the first part. Fine. Then second step is if we take this initial point, this point, I mean, which we have chosen as a reference point, and draw a circle. Now, what we do is let us draw a circle of radius k I mean, the radius is equal to magnitude of this k vector, and we draw a circle. Fine. Rather, in case of 2D, we will draw a circle. If we are dealing with, actually, we are dealing with the three-dimensional crystal, so we will draw a sphere of radius k. Now, where all we will be getting diffracted beam, or where all we will be getting maximum intensity, at what angles we will be getting maximum intensity, can be obtained from this condition. Now, what is the condition is that you choose that, okay, how many points are lying on this surface of this sphere, right? How many points are lying on surface of this sphere? So this one definitely will be lying on surface of this sphere, because we have chosen our radius to be terminating at this point. So definitely this is going to appear on the surface. Then there may be this second point, right, which is also lying on the surface. So all those points. So okay, first of all, let us try to understand what is the special relevance of those points lying on the surface. So basically, these are the points which do satisfy diffraction condition. These are the points which satisfy diffraction condition. Why so? Let us assume this is k dash. Now, let me not say this is radius of this sphere, but let us say this is our k dash vector, the vector of the scattered X-ray beam. Correct? Then, if this is k, if this is k dash, what is this? If you try to apply the triangular law of vector addition, this will be nothing but delta k. Correct? This will be delta k. And by the way, what is this delta k equal to? This is equal to nothing but g, the reciprocal lattice vector. Because what is reciprocal lattice vector in the reciprocal space? It is any vector connecting any two points in the reciprocal space. So this is g. So this means all those vectors, that is k dash vectors, the points on the surface of the sphere, to the lattice points lying on the surface of the sphere. This sphere is also called evolved sphere. Fine. Actually are representing the directions at which you will be finding maxima in the X-ray intensity, which is scattered from the crystal. Then you may find some other point, and that will also satisfy. So this actually gives you the value of angle 2 theta. Means, what is angle 2 theta? 2 theta is actually the angle between incident beam and the scattered beam directly. So 2 theta is the angle between incident beam and scattered beam. So this is what we call the evolved construction. Is this part clear? I mean, that I already talked. I mean, this has to be delta k equals g. Okay, is this part okay, or is there any question from this portion? Is the evolved construction and way to understand diffraction pattern from reciprocal lattice clear, or is there any question? Yes, please. Harish is asking something. It gives information about orientation. Is it also going to give us location of electrons and atomic position? Definitely, it will give us the location of atomic positions. There's nothing like location of electron. I mean, we can't locate electron. I hope you are aware of that uncertainty principle, isn't it? So we can't exactly talk about the physical location of electron, but yes, we can talk about electron density. So we actually talk of probability of finding the electron at specific point in the space. Um, at peak maximum probability, I mean, it's not as straightforward. What do you mean by peak and probability? Still, I mean, X-ray peak as such has nothing to do with the electron density peak directly. Means it doesn't mean there is a maximum probability of finding electron at such, say, a particular point in the space. No, I mean, this peak has a lot to do with the how are atoms arranged and how are the electrons arranged in the unit cell. Of course, NR. I hope you remember that expression, that electron density is sitting there, but a peak doesn't represent a very sharp electron density at a particular point in the unit cell. So I don't know if you are misinterpreting it that way, then this is wrong. Yes, the peak actually follows from the uh, diffraction condition, as well as what is or how the electron density is distributed in the unit cell. That is fine. And then you are asking, okay, can we find out atomic positions? Yes, of course, because if you go back to that expression for structure factor, okay, this is yesterday's thing. So if we go to the expression for structure factor, so it has atomic form factor. So this is now, I mean, I have hired this slide from yesterday's presentation. So this atomic form factor is something that has something to do with the electron density. Atomic form factor has something to do with the electron density. I hope you remember yesterday's slide. Those who have missed it, I will be uploading these video lectures. I think I am not doing it, so I will be doing it this weekend completely and properly topic wise. I will upload it on Google Classroom, so that if you have missed something, you can go back and see those. So this actually F takes care of that electron density part. And where are atomic positions coming in? So they are coming in structure factor, right? So when we were doing for say 0, 0, 0, atom sitting at 0, 0, 0, 0, half, 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 0, half, and half, half, 0, then all those appear here in structure factor. So once we know structure factor, this is related to the intensity. I hope you remember. This is related to the scattering wave amplitude. What was scattering wave amplitude? F was n times S, where n was number of unit cells and S is structure factor. Well, this structure factor then is containing electron density related information as well as information of atomic positions. So yes means from X-ray we can do a reverse calculation actually. So there are two ways. I mean, if you know how are electrons distributed in atom, we can calculate the atomic form factor. Then if you know, okay, where are atoms present in the unit cell, then we can calculate structure factor. And if you know what is structure factor, then we can calculate the scattered wave amplitude and hence intensity of X-rays. That's how you can theoretically predict X-ray of a crystal to be. That's one way of doing it. Other way of doing is doing a reverse calculation. I mean, suppose we don't know the atomic positions and we do measurement of X-ray diffraction pattern of any crystal. Then from that, we try to calculate all these parameters back. So the task is not very straightforward. Yes, it requires solving a lot of models. You have to try a lot of things. Like, okay, you first try to fit your X-ray diffraction pattern to one specific model of a unit cell. If it reproduces the experimental pattern, fine, or you may try it with the different model of the unit cell and so on. So anyway, that's a different aspect. But yes, that is how we can obtain the information regarding atomic positions in the unit cell. And of course, we can also calculate electron density in the unit cell. Is this clear, Harish, or is it okay with others as well? Or is there any further question? Fine. Is there any question? Any other question? I mean, from anyone else? Yes, Sandeep or Rahul. We have two new research scholars who are today attending the class with us. Sandeep and Rahul. Is it clear? I mean, maybe you have done it better earlier as well. Okay, fine. So having done this, so I'm sure you all have done this structure factor calculation for FCC, right? So in FCC, what you will be finding is that only certain specific peaks will be observed and others will be absent. So what all was the condition? What was the condition? Have anyone done this for FCC? What was the condition for BCC, which we have done yesterday? For BCC, what was the case? When I think all the indices, I mean Miller indices of the planes was odd. I mean sum of Miller indices of a particular plane was odd. So there was no intensity, right? the intensity of scattered X-ray was 0. So we won't be observing something like 100 peak or 111 peak in BCC structure, correct? But what about that situation for FCC? Have you done this? What happens in this? There's such relationship. Homework to you, Harish. Have you done the homework? Am I audible? Okay, okay. I mean, let me ask you for putting up your attendance. So, Sandeep and Rahul, how do we mark our attendance? Is that we type our roll number in this chat box. Fine. So that is just marking of your attendance. For FCC, all odd or all even, I think. This is just, you should work out this expression actually. Fine. So basically, okay. Now, I hope you remember e raised to the power minus iota n pi. This is an expression like e raised to the power minus iota n pi. So, because these are two integers, v1, v2, v3 are some integers, correct? So, sum of any two integers is also integer, correct? And what was the value of e raised to the power minus iota n pi? So there were two situations, when n is even and when n is odd. I mean, let us say this, the sum of these two is n, let us say small n, some integer, v2 plus v3 is suppose n, correct? So what will be e raised to the power minus iota pi for n is equal to even? What was this to be equal to? E raised to the power minus iota n pi. When n is even, what will be e raised to the power minus iota n pi? Yes, students, we have done it in yesterday's class. Please. Oh, come on, I'm waiting. This we have already done yesterday. Am I audible there? I didn't see even your roll numbers, your attendance. Oh, come on, mark your attendance at least. I get confused whether I am audible or not.
Yes, sir, you are audible. Hello.
Okay, this is
Hello.
one. Means very good. So it will be happy if
You are not audible, sir. Your
you,
sound
I
is
mean,
breaking. Hello.
respond without much delay. Yeah, Harish, you are audible. Fine. One. Fine. When n is simplest way is
Okay.
power iota minus. Yes, yes. Is it okay?
Okay, sir. Okay.
Ah, today. Okay, so today we are facing a lot of issues with internet. Anyway, no problem. Let us continue. So this will be 1. When it is even, when n is even, this will be 1. When n is odd, this will be minus 1. Correct? E raised to the power, say, say minus n is equal to, let us take 1. So e raised to the power minus 1 pi iota, or e raised to minus iota pi. This will be cos be 0. That's okay. Sin n pi. So cos of pi is minus 1. So this will be minus 1. Now let us try to interpret this. So if v1, v2, v3 are all even, let us assume that V1, V2, 2, right, is equal to 6. Am I audible? Ah. Okay, anyway, let us note V1 is equal to 2. Okay, this will be 4f because V2 plus V3 is even number, is also an even number, correct? So if, okay, V1, V2, V3 all are even, so the sum is always going to be even. So this will be even, this will be even, this will be even. So all of them, all these 4 terms will give you 1. So the structure factor will be 4f. Very good. And if V1, V2, V3 are all odd, so means you will observe something like 2, 4, 6, 2, 2, 2 peak. All these kind of peaks are observed because they are giving you a non-zero structure factor which is equal to 4f. What happens when all the indices are odd? What happens when all the indices are odd? Am I audible now? Again, okay. For odd indices, it is also again going to be fine, correct, 4f. Now, okay, let us take another example. Suppose one of the index is odd, other 2 are even. Suppose one of the index is odd, other 2 are even. This actually was your homework. I mean, you all should have come with this done. But anyway, so please do it. These are quite simple exercises. Okay, let us take another example. If one of the index, one of the Miller indices is odd and other 2 are even, something like 1 to 2 peak. What will be the situation in that case? What will be the structure factor? It is going to be 0. Why? Because sum of one odd and one even number will be odd. So at 2 places you will be finding this value to be odd. This is already 1. So at one place it will be even because you have 2 even indices, correct? So this will be 0. Let us do it other way. And what is the other way of doing it? Is that let us take one index is even and 2 are odd. Let's do it other way now. I mean, earlier we assumed that, okay, 1 is odd, 2 are even. Now let us assume other way. So if 1 is even, 2 are odd. So what will be the structure factor in that case? Again 0. Yes, very good. So now I think you have answered the question. So what all peaks are visible or observable for a FCC lattice? All those peaks for which the Miller indices are either all even or all odd. In case any one of the Miller indices is even and other 2 are odd, or vice versa, then we won't be observing all those peaks. So that is how structure factor is helpful in determining that, okay, which specific peaks are going to be absent. At least we can tell without doing any detailed calculations, only by looking at structure factor, that which particular peaks will be absent. So that is straightforward. Now What will be the intensity? For that, we also need to get, I mean, for the peaks which are which are to be observed, we have to calculate the atomic form factor as well. Then that will be a complete structure factor. And then from the complete structure factor, then we can calculate the intensity, because from there will follow the scattered wave amplitude, and then amplitude star amplitude will give you the intensity. I hope that is clear. Is this fine till now, or is there any question? Okay. So today actually I had planned to go a little beyond this, and then we had to discuss this different zone schemes. Okay, how many of you have studied this extended zone scheme, periodic zone scheme, reduced zone scheme? How many of you have done this? Yes, those who have done it, please type yes, sir, or yes only. Am I audible? Okay, no. Yes, type your response. Let me at least know the feedback so that I could accordingly plan my lectures, so that I could actually, I mean, keep the contents brief or detailed, depending on your reference, your response. Others? Oh, most of you haven't done. What about Rahul and Sandeep? Rahul, have you studied it somewhere? I mean, have you done it in your PG classes? Rahul have done. Sandeep, you also have done. Very good. So, well, I mean, since we almost have consumed our time just to do your homework, I would like you to ask your questions. I mean, specifically, let me ask Rahul and Sandeep, if you had doubts related to this concept, you please put in your questions so that in my next class I can try to incorporate the answers to those questions as well. Were you having some doubt, or this was clear to you? Rahul, Sandeep, I hope you can hear me. I mean, you have some questions related to this topic? Sandeep has no questions. Rahul? Yes, sir. This was fine, but different zone schemes, a recap will be helpful. Fine, recap I will be doing. But I just want to see if you have a specific doubt or question so that I can address that. Or it just is a quick recap. Fine, if there is no question, I will be presenting this. This is a very important topic actually, and this relates to what we call Brillouin zone folding. Have any one of you heard of this term, Brillouin zone folding? Sandeep, Rahul specifically, and other students as well. Have you heard of the term Brillouin zone folding? So if you haven't heard of Brillouin zone folding, then you have missed very important aspects of these Brillouin zone schemes. Anyway, so tomorrow we will be, or in next class, we will be discussing about all these things. And let us hope we will complete it tomorrow itself. Okay, then that's all for today. It was just a very little content as such, but I hope you understood at least the structure factor properly, and various ways to understand X-ray diffraction from a crystal by employing reciprocal lattice. Fine. So that's all for today. Let us see you in the next class. Have a good day.